All right, we are going to look at escape velocity. Escape velocity is defined as the velocity needed to leave a surface of, say, a planet with, such that as you go higher and higher, you slow down, and you slow down to the point where your velocity is 0 when you reach infinity. Okay, so the idea is if I throw this ball up, it comes back down. If I throw it up harder, it takes longer to come back. The idea here is that if I throw it hard enough, it'll never come back. It'll reach infinity and come to a stop. Okay? So how do we do this? Well, we're going to set up an energy conservation problem. We're going to assume we're throwing it off something like the moon where there's no atmosphere to slow it down. And we're going to ignore any other gravitational forces anywhere else in the universe. We're just going to say the gravitational force of our one object is all we're concerned about. So we're able to say that the kinetic energy plus the gravitational potential energy at the surface is going to equal the kinetic energy and the gravitational potential energy at infinity. So this is at the surface, and this over here is at infinity. All right, so we'll find that when we go to infinity, we want it to be stopped so the velocity equals 0. Also, when we plug in the universal gravitational potential energy, we find that if we plug in infinity for r, this is also 0. Okay, so what we're left with over here is we're left with 1/2 m times the escape velocity squared plus the gravitational potential energy negative g big M little m over the radius of my, say, planet or whatever it is, equals 0. And you can see if I plugged in infinity here for this, where this r is, that value would essentially be 0. Okay, so we're going to go ahead and keep solving this. So I'm going to get rid of the mass so it doesn't matter what object I throw, whether it's a satellite, whether it's a tennis ball, the mass is not required for the calculation. We're going to go ahead and move this over the other side, multiply by 2 to get rid of the 1/2, and then take the square root. And so the escape velocity is going to be the square root, big G, big M, over r, and I had to multiply that 1/2, get that out of there, so multiply by 2. And so I get this, and so the escape velocity from any planet or object is going to be 2 times the gravitational constant, universal gravitational constant, times the mass of the object divided by the distance center to center that it starts at. Okay, and since we're at the surface, we're using a capital R here. So let's try this out, see what kind of numbers we get. So we're going to use the moon. We're going to try and figure out what is the escape velocity for the moon. So the idea is the moon is much smaller. Gravity's a lot less on the moon. So we should be able to maybe launch rockets a little easier from the moon. Okay, so how much easier? What is the escape velocity on the moon? All right, so we bring up our table of astronomical data, and I found the mass of the moon and the radius of the moon. This is the equatorial radius. It's not much different than the polar, but that's the one I picked. So we have the escape velocity is equal to the square root of 2 times big G times that mass, 7.35 times 10 to the 22nd, all divided by 1.74 times 10 to the 6th. Plug that in, you get an escape velocity that seems pretty darn big. 2,370 meters per second. To give this a number that maybe you can wrap your head around, this is pretty much Mach 7 here on Earth. So 7 times the speed of sound here on Earth would be the speed you need to project something with on the moon so that it would never come back. So it's still, even though we go to the moon, you're like, gravity's a lot less, it still has a huge escape velocity. Okay? So escape velocity is not something we usually use to launch rockets with. We're going to have to not just instantly do that, we're going to have to give it energy over time. Okay? That's that.